Hi there, my name is Andrew Brown, and welcome to Oxidation and Reduction Reactions. As we move through the review of material, we'll cover, generally, oxidation states of some common molecules, the reactions that these molecules typically undergo, grouped according to their effect on oxidation state. Then we'll show you a few different degrees of oxidative cleavage reactions, and finish with the reactants and reagents involved in reduction. After watching this video, you should be able to answer questions like this one, which requires you to recognize a potential reduction or oxidation reaction based on the reactants and products involved and predict a suitable reagent. In order to understand redox reactions, we must have a firm grasp on oxidation states, because that's what will be changing. At the most basic level, an atom's oxidation state describes its relative electron density. If we examine isopropanol shown here, bonds between the central carbon and the methyl groups are relatively nonpolar. The carbon-oxygen bond, however, is decidedly polar. To determine the oxidation state of the central carbon, treat the carbon-oxygen bond as if it were completely ionic in character. Remember for general chemistry that in such a bond, the more electronegative atom, oxygen in this case, will attract the electrons in the bond closer to it, creating a hypothetical -1 charge on the oxygen atom and a +1 charge on the central carbon atom. Turning now to acetone, the double bond between carbon and oxygen has double the electron polarizing effect as the single bond had in the previous example. This gives it an oxidation state of +2 and makes acetone the more oxidized species. Now, if you wanted to compare oxidation states of carbon atoms between several molecules, we want to focus mainly on the bonds between carbons and more or less electronegative atoms. In this example right here, each additional bond between carbon and oxygen increases the oxidation state of carbon. Therefore, we can derive the following hierarchy. Okay, now that we know how to quantify oxidation state, we can explore some reactions that alter it. In ethanol, just as isopropanol, the central carbon has a +1 oxidation state due to its polar covalent bond with oxygen. Conversion to ethanal should increase the central carbon's oxidation state, just as we saw in acetone. We'll return to the reagents responsible for these types of transformations in just a moment. As we convert ethanal to acetic acid, notice we gain another bond to oxygen and achieve a corresponding increase in oxidation state. So what about the reagents now? First of all, any reagent that causes an increase in oxidation state is referred to as an oxidizing agent or oxidizer. The first reagent here, chromium trioxide, is dissolved in pyridine and functions as a weak oxidizing agent. The second reagent, a dilute solution of potassium permanganate, is another weak oxidizer. This is a good place to make a note about memorizing reagents. Don't. Rather, make note throughout this video of the structures common to oxidizing and reducing reagents. That way, if the MCAT throws out some little-known reagent, you'll be ready. Notice here that both reagents contain bonds between high oxidation state metals and oxygen. Notice also, however, that each oxidizer only raised the central carbon's oxidation state by 1. This is why we refer to them as weaker oxidizing agents. If we wanted to convert ethanol to acetic acid all in one step, we would need a strong oxidizing agent. Thankfully, this first one is easy to remember, as we have just raised the temperature and concentration of our familiar potassium permanganate. So that's all we have to cover for oxidation reactions affecting a single atom, but the MCAT will also test you on oxidation of bonds within a molecule. When a pi bond is oxidized, one possible outcome is the cleavage of the entire double bond. In this example, whereby 2-methyl-but-2-ene is treated with ozone, the reactant is split into two products that display carbonyls where the double bond once was. Now, ozone in a reductive workup of zinc or dimethyl sulfide is a weak oxidizing agent, denoted by the fact that the products are not in their most oxidized forms possible. See, the central carbon in an aldehyde or ketone has an oxidation state of +2. If we were to use a stronger oxidizing agent, such as ozone dissolved in hydrogen peroxide, we can expect a carboxylic acid product which would have an oxidation state of +3. We just saw an example of an oxidation reaction in which a double bond was cleaved entirely, but that's not the only possible outcome for oxidation of pi bonds. Indeed, epoxides and glycols, which we'll visit in just a moment, represent products for which only the pi bond and not the underlying sigma bond is cleaved. In order to create an epoxide, you will need to use a peroxy acid. When we treat with metachloroperoxybenzoic acid, or MCPBA, a common peroxy acid, the same reactant as in the previous example will instead be converted to the epoxide 2,3-epoxybutane. As you can imagine, the three-membered ring common to epoxides is extremely reactive. which underscores their usefulness in synthesis reactions. Now as we explore glycol formation, you'll be struck by the similarities with epoxide formation. Osmium tetroxide, however, is the reagent here, and it makes vicinal syn-diols out of alkenes, like this one that we've been studying in the past few examples. The product, 2,3-diol, is thus referred to as a vicinal diol, or just glycol. Vicinal refers to the placement of the hydroxyl groups on adjacent carbons, while being syn means that they are also on the same side of the carbon-carbon single bond. Now, if you wanted to cleave the remaining carbon-carbon sigma bond, you can imagine that treating the glycol with another oxidizing agent would not just yield two alcohols. As we'll see here, subjecting the glycol to periodic acid or sodium periodate cleaves the carbon-carbon single bond to yield a pair of aldehydes. So that was a lot on oxidation reactions. Now we're going to turn to their counterpart, reduction reactions. Because they are essentially the reverse of oxidation, we won't need to go into a ton of detail here about the mechanism. However, watch as we reveal some reagents in reduction reactions and notice the interesting pattern that starts to emerge. Let's begin with a simple reaction. The blue carbon in 1-phenylethanone has an oxidation state of +2. When the carbonyl is reduced to an alcohol, the blue carbon's oxidation state falls to +1. Classic reduction, right? The reducing agent here is sodium borohydride, and the pattern I mentioned earlier refers to the significant number of hydrides surrounding this reagent. It is also important to note that sodium borohydride is a little on the weak side. If you want to reduce a carboxylic acid such as benzoic acid, you'll need something a little stronger like lithium aluminum hydride. It is capable of reducing more oxidized reactants into alcohols. Okay, so that does it for the material this video will review. Now let's turn our focus to employing those concepts on some sample questions. This first one is asking you to predict the reagent necessary for the given reaction to proceed. The answer should be C. In order to answer this one, you must first determine whether we are dealing with an oxidation or reduction reaction. The epoxide in the product is our clue that this is an oxidation. While 3 oxidation agents are listed among the answer choices, remember MCPBA is the only one that forms epoxides. This next question asks you to predict the product from a given set of reaction conditions. In order to solve this question, it's helpful to visualize the initial reactant, 1-methylcyclohexane, or even draw it out on your scratch paper. When treated with ozone and zinc, we expect the double bond to be cleaved. Because this combo is a bit weak, 1-methylcyclohexane should only be oxidized to the point of ketone or aldehyde. Now count up the number of carbons with which we started and match to C. We're almost finished, so let's take a moment now to review what was covered in this video. After defining oxidation states, we took a look at some reactions that increase them. Our example reactions showed ethanol being oxidized to ethanal and in turn acetic acid by a pair of weaker oxidizers. We saw that the ethanal intermediate could actually be bypassed by using a stronger oxidizing agent. For the subset of oxidation reactions that result in a cleavage of pi bonds, we first observed how ozone cleaves them into carbonyls, and then we moved on to epoxide formation, which is usually catalyzed by MCPBA and results in the characteristic 3-membered ring structure between vicinal carbons. Glycol formation was catalyzed by osmium tetroxide and resulted in vicinal syn-diol formation. However, we saw that osmium tetroxide isn't strong enough to cleave all the way through the double bond, that additional oxidizers are needed for that. And finally, we looked at reduction reactions with reagents of varying strength, emphasizing that a strong reducer like lithium aluminum hydride can reduce just about any functional group back to an alcohol. Thanks very much for watching, and good luck in your continued MCAT study.